In this video, we're going to learn about the mean value theorem. First, some context. We learned from the extreme value theorem that on a closed interval, a continuous function has an absolute max and an absolute min. Then we learned about critical numbers, which is where to look for the local max and the local min. What we don't know is how can we tell if a critical number corresponds to a local min, a local max, or neither? Well, we're going to have to step back first from thinking about critical numbers and think about something else. We're going to start with a theorem called Rolle's theorem. Now, the geometric idea is pretty clear. If you've got a smooth function and you've got 2 points on the function that have the same y coordinate, so if you connect them with a line, the line is horizontal, then somewhere between A and B, there's got to be at least one point on the curve where the tangent line is horizontal. And you can see how that connects to Fermat's theorem, that if we start with the same y coordinate, end with the same y coordinate, then that means we either went up or went down in a smooth way. And when we make that turnaround point, that has to correspond to a local max or a local min. And at that point, the tangent line is horizontal. In this example, there's actually 2 numbers between A and B where we have a horizontal tangent line. So let's look at the formal statement. We need to have a function which satisfies the following 3 conditions. F has to be continuous on the closed interval, has to be differentiable on the open interval. And really, that's what we mean by saying that we have a smooth function. And we need to have the y coordinates at A and B equal to each other. If we have all 3 of those conditions, then our conclusion is that there's a number C between A and B where f prime of C equals 0. We can also think of this in terms of a physical interpretation. If we have a displacement or position function S of t, and it represents a particle moving in a straight line, if you have 2 different times where you have the same position, so at time equals A and time equals B, then the particle must have started at a given position, gone somewhere else, and then came back to the same position. Well, it's always moving in a straight line, so the only way it can come back is it must have stopped at least once. And when the particle is stopped, its velocity is 0, so S prime would be 0. Now, the mean value theorem is closely connected and, in fact, equivalent to Rolle's theorem. You can use Rolle's theorem to prove the mean value theorem, or if you know the mean value theorem, you can use it as a special case of the mean value theorem. Now, the geometric interpretation of the mean value theorem, again, is pretty straightforward. If you have a smooth curve and you connect 2 points with on the curve with a straight line, that's our secant line, then at some point between those 2 points, there's a point on the curve where the tangent line is going to be parallel to the secant line. So you can see how Rolle's theorem would be a special case of this. The physical interpretation, again, has to do with velocity. So again, if we have a particle moving in a straight line, and it has an average velocity of 10 meters per second between 2 values of time, then at some time between those 2 values, it must have been traveling at exactly 10 meters per second. Think about this. If you drive 120 miles in 3 hours, That means your average velocity is 40 miles per hour. It makes sense that at least once during that time, if you look down at your speedometer, it would be showing 40 miles per hour. So let's look at the formal statement for the mean value theorem. Suppose that f is a function which satisfies the following two conditions. F is continuous on the closed interval AB, and f is differentiable on the open interval AB. Again, we have to have a smooth function. No sharp corners, no jumps, no holes. Then there's a number c in the open interval AB such that f prime of c equals the difference quotient f of b minus f of a all over b minus a. And we'll recognize that f prime of c, that's the slope of the tangent line, and f of b minus f of a all over b minus a is the slope of the secant line. And I can rewrite that as f of b minus f of a equals f prime of c times the quantity b minus a. And so if I think about it in this final way, then there's some natural results. If f prime of c equals 0, then f of b would have to equal f of a. So if f prime is 0 for all x in an interval, then no matter what two numbers you choose in the interval, they're going to equal each other. And so in that case, f would have to be constant. And that would say if you have two functions whose derivatives equal each other, then their difference has to be a constant. Really, that's just saying f minus g is some function h, and if h prime of x equals 0, then h prime is constant. But saying that f minus g is constant just means that f of x is g of x plus k. So let's look at an example where we can apply the mean value theorem. We're going to use the mean value theorem to show that there is exactly one positive solution to the equation sine of x equals 2 minus 2x. So when we say exactly one, we mean one and only one. There has to be one, but there can't be any more than one. And we're not actually trying to solve the equation. We're just simply trying to show that such a solution exists. So if we think about it, there's two parts to the question. The first part is we have to show that there is a positive solution. And we'll use the intermediate value theorem, just like we did before in chapter 1. And then we're going to show that there cannot be two positive solutions. And for that, we'll use the mean value theorem. So let's do the first part. And here I just did it all in one step. If we want to show that there's a positive solution, then I need to find two values where, well, first of all, I need to rewrite the equation in terms of a function. So f of x will be sine of x minus 2 plus 2x. I find two x values where the function value is positive at one end, negative at the other end. So f of 0 is negative 2. F of pi over 2 is pi minus 1, which is positive. So since 0 is between f of 0 and f of pi over 2, then by the intermediate value theorem, there's a number u between 0 and pi over 2 such that f of u equals 0. And that u is our solution. Now let's do the second part. We're going to show that there cannot be two positive solutions using the mean value theorem. So suppose that the number v is a different positive number where f of v equals 0. Then by the mean value theorem, there has to be a number c, which is between my two solutions, u and v, where f prime of c equals 0. But if we look at the formula for f prime, it's going to be cosine of x plus 2. That can never be 0. The smallest that cosine of x can be is -1, and -1 plus 2 is still positive. So we get a contradiction. And when we get that contradiction, that means our original statement must be false, that v is a different positive number, f of v equals 0. So 2 little footnotes. All right. In this case, we're really using Rolle's theorem, but Rolle's theorem is a special case of the mean value theorem. And this whole technique that we used in our second part is an example of proof by contradiction. You make an assertion or an assumption. You show that that assumption leads to a contradiction, which implies that the original assumption must be false.